Okay, this is the last video for chapter 23. We're going to be looking at the electric field for a line of charge, or for continuous charge distributions in general. Whereas if you have a collection of point charges, we call that a discrete charge distribution. If your source charge, though, is spread out continuously, it's a continuous charge distribution. And we're going to base this on the field of a point charge. Remember, the electric field equals kq over r squared. But if we imagine a continuous line of charge, so we're going to say like this, it has length L, and what we'll do is we'll say that there is a charge plus q spread out over the line of charge. What we'll do is we'll break it up into a lot of small point charges, dq. So instead of treating it as a line, we'll treat it as a series of very closely spaced point charges. Now if we want to find the electric field at, say, this point here, which is a distance capital R away from the middle of the line, that point charge dq there will, if it's now a distance little r away from the line, will produce an electric field dE that points like that. And all of these point charges dq will produce their own dEs. And what we're going to do is we're going to add up all of the dEs to find the net field at that point. And because electric field is a vector, this can be a real pain if you don't have large degrees of symmetry. But notice I specified this as a distance r from the midpoint of the line. And that means for this dq here, there's another dq on the other side that produces a field pointing like that. And for this particular situation, the symmetry means that the x components cancel out. And we only need to find the y components of all the dEs, which makes things considerably easier. If this wasn't symmetric like this, we would need to add up the x components and the y components, and both of those are going to work out to be different integrals, which admittedly are not terribly complicated ones, but if you only have to do one integral instead of two, that's just fine. Now keep in mind, when we say add up, when you've got lots of very small things that you're adding up, what you're really doing is you're integrating. And let's see how this works in practice. I'm going to work through this example in the rest of the video. So remember, we've got our continuous line of charge, which is the length of L, and we're going to define something called linear charge density lambda, is the charge per unit length. So in other words, it's dq dx. And if lambda is constant, which we're going to assume that it is, lambda also equals the total charge divided by the total length. And so here's our field point here. It's a distance capital R away from the midpoint. Here's our dq, which is located at a distance x away from the center and has a width dx. And that means that if dq has a width dx, dq and dx are related like this. So we can say that dq equals lambda times dx. Okay. And so our expression for dE, which is the dE is equal to k times dq divided by r squared. But remember, we are only considering the y component of dE. And so if we look at this expression here, the y component of dE is adjacent to that angle theta. And so we have k times dq over r squared times the cosine of theta. What we're going to do is we're going to integrate dEy. But in order to do that, everything that's changing has to be expressed in terms of a single changing variable. And we're going to make our variable of integration x. And that means we need to express dq in terms of dx. That's what this whole charge density thing is about. We also need to express r and theta in terms of x, because you notice as you change x, this distance little r is going to change, and so will the angle theta. And since when we integrate, the only thing in the integral that is allowed to not be a constant is our variable of integration, which is going to be x. And that's what we're doing on the next page. So keep this idea in your mind. I'm going to draw this out again. So that is r, there's dq, there's little r, dE, and that's theta. So the first thing, we know from the charge density equation that dq equals lambda dx. And so dEy now becomes k lambda dx over r squared all times cosine theta. The next thing we'll do is we'll look at this triangle here. That's x. And we'll ask, okay, cosine theta is adjacent over hypotenuse. Adjacent for this triangle is r. Hypotenuse is little r. And so now we can call it, say that this is k times lambda times r dx over r cubed. We've gotten rid of the theta. That's good. Unfortunately, we still have this little r, which we want to express in terms of x. K lambda and r are all constants, so we're fine with them being there. Dx we're fine with. But little r we need to deal with. And again, we'll have to use geometry. We'll use the Pythagorean theorem, where r squared equals capital R squared plus x squared. And so dEy we're going to express as k lambda r dx over big R squared plus x squared, all raised to the 3/2 power. Now we're going to integrate. And we'll pull all the constants out at the front, k lambda r, the integral of that. And then we ask, okay, what are our limits of integration? Well, we're integrating from here over to here. So over here, this will be at x equals negative L over 2, and this over here, x equals positive L over 2. So that is our integral. But now we'll say, okay, symmetry. Because this is symmetric about the midpoint, we can say that the integral over the whole thing is equal twice the integral of half of it. So this is 2k lambda r, the integral of 0 to L over 2 of all that. At this point, we have done all the physics. We've expressed dq in terms of dx. We have expressed theta and r in terms of x. And we've set up an integral that we can evaluate. And that's what we're doing on the next page. So the integral ey equals 2k lambda r 0 to L over 2 of all this. And this integral is not one I remember how to do. However, I do know that in your textbook, in the front cover, there are some commonly used integrals, and one of them is this one. And so you look up in the table of integrals, and you end up with 2k lambda r times x over r squared times the square root of x squared plus capital R squared, and we'll integrate from 0, and we'll evaluate at 0 and L over 2. And that works out to be 2k lambda r times L over 2 times r squared times L squared over 4 plus r squared. And a little bit of simplification, it works out to be k lambda L over r square root L squared over 4 plus r squared. And there is our equation. Now, something you should try on your own is prove that as L approaches infinity, in other words, as the line of charge becomes infinitely long, the field works out to be 2 lambda k over r. It's an interesting exercise. But what I'm going to check tomorrow is question 7 and problem 20, which deal with the electric fields due to continuous charge distributions.